Hello students, in the last video we have discussed about post correspondence problem to prove the undecidability. Of course, even the post correspondence problem is undecidable and also used to prove other problems are decidable or undecidable. In this video we'll discuss about the Chomsky hierarchy of languages. Of course, we have used all those languages earlier, but how they are related. So first we'll go with the grammars. See, the regular grammar, context-free grammar, context-sensitive grammar, and unrestricted grammar. The type number, type 0, type 1. And see, we can say that the languages, regular grammar going to accept the regular languages, contextual languages going to accept the contextual languages, context-sensitive grammars are going to accept the context-sensitive languages, unrestricted grammars are going to accept the recursive enumerable languages. And we have a subsets in CFL and REL. So if you want, you can even go with the more generalized version like this: RL, DCFL, okay, CFL. CFL is having another subset. Then we are having CSL, and RCL is also unrestricted grammar. We are having two types. One is RCL, and another one is REL. If something which is not even accepted by the Turing machine, those are called as non-recursive enumerable languages. These all are completely undecidable problems, right? So that's what we have discussed there. So we have other properties also. Let me just go with the four whatever we have discussed, right? So instead of subset, we can apply the same rules, right? The regular grammars are going to accept regular languages. Contextual languages grammars are accept contextual languages. Here CSL, here REL. See guys, the same way the unrestricted grammars, the machine we can take it, Turing machine, and context sensitive languages means we are having the linear bounded automata, the restricted Turing machine, and contextual languages means we are having the PDA, that is push down automata, and regular grammars or regular languages are going to be accepted by the finite state machine or finite automata, right? So then what is it? What is the relationship between all these things? So we'll discuss, then we'll go for the definition of each and every grammar. Okay, first of all, let me go with the subset superset theory, guys. Assume that we are having a subset here, okay, and the superset. Let me write it. A second. Right. See, assume that we have a subset, and you can apply it for even compiler design parsers also. Same subsets, and not only this, whatever the diagram earlier I've written, DCFL, CFL, we use some, right? We can apply it. Assume that this is a subset, naming that X, right? And this is a subset naming that Y. So we can say that X is subset of Y. X is subset of Y. Now assume that we have some languages in X, right? I'm giving some names to the languages in X, like we are having I, J, K, and in Y, L, M, N, P. Assume that. Okay. So what are the elements of X here? Right. So the X set is having three elements: I, J, K. And the Y set is having five elements. Those are, sorry, I, J, K. Even Y contains I, J, K, and also L, M, N, P. So we are having total 7 elements. Here we are having only 3 elements, right? Then what is the property? We are having 4 properties here, guys. The first property is every X type of element is also a Y. If it is in X, must be in Y. Means we can say that the first property here, every X type must be a Y type. Means every subset type. You can write here. So first statement, every subset type must be superset. Must be superset. Means we can say that every X type is Y type. So every regular is CFL, every CFL is CSL, every regular is CSL, every regular is REL, every CFL is, this is the relationship, like that. Okay. Then the second one, if it is in y, what about in x? May or may not be. For example, I is in y in x, j is in y in x, k is in y in x. Some are in x, but L is in y but not in x. M is in y, not in y. So in a general, if something in y may or may not be in x. So if it is a y type, may or may not be x type, the second one. So if it is superset type may or may not be subset type. May or may not be subset type. Means what? Every CFL is may or may not be regular. Every CSL is may or may not be CFL. Every REL is may or may not be CFL, or every REL is may or may not be regular. Right? There's a third property. And sorry, second property. Third relationship between the languages. See guys, if in a language or a value or element is not in X, it may or may not be in Y. For example, take first element L. So L is not in X, but L is in Y. So if something is not in X, maybe in Y. You take another property like R. R is not in X, and of course R is also not in Y. R is somewhere else outside of Y, that we are not worrying about it. Means if it is not X type, may be Y type, may not be Y type. It may be in the Y set or may not be in the Y set. So third property, if not subset, right? If not subset, may or may not be superset. May or may not be superset. Means if it is not regular, may or may not be CFL. If it is not CFL, may or may not be CSL. If it is not CSL, may or may not be REL. The fourth one, right? For example, if which is not in Y must not be in the X. For example, R. If R is not in Y, must not be in X. If take T, if T is not in Y, must not be in the X. So that's the fourth one. If not superset type, must not be subset type. Must not be subset type. Four problem means if not CFL, must not be RL. If not CSL, must not be CFL. If not REL, must not be. So this is a relationship between the languages and hierarchy also. Same, every regular grammar. You can apply it, guys. Not only this, whenever you have these kind of diagrams, right? I may give some other like this. See, RCL, REL. If I give that, you apply it. Subset, superset. Every RCL is REL. Every REL may or may not be. You apply the four properties, whatever I've written here. Okay. So that's about the hierarchy. Now let me go with the definitions of grammars quickly. So what is unrestricted grammar? The name is itself even saying that no restrictions at all. If you have left hand side and right hand side, you take whatever you want on left hand side, whatever you want on right hand side. Like alpha belongs to n plus t whole star and beta belongs to n plus t whole star. You take whatever you want. But the only condition you should do here, the property, not the restriction, that the alpha must contain at least one non-terminal. At least one non-terminal. Why means if there is no non-terminal, if everything is terminated here, then it cannot derive the right hand side. But the property of grammar is the left hand side must derive the right hand side. To do that, we should have at least one non-terminal. You may have any number of terminals, non-terminals. Okay, the size is left hand side maybe more than that, less than that. Use epsilon wherever you want. There is no restrictions, right? Then coming to the type 1 are context sensitive grammars. See, the context sensitive grammars should follow these rules, right? So the first and the foremost condition of the context sensitive grammar is same, guys. Here the alpha tends to beta. Of course, the alpha must contain at least one non-terminal left hand side. That's a property of the grammar, not the condition. And see, the length of the left hand side must be less than or equivalent to the length of the right hand side. There's the first property. The length. You may have any symbols here and you may have any symbols here. So the first rule, whatever according to this, means alpha comma beta belongs to n plus t whole star. You can take whatever you want, more than one symbol, but this is the length of the left hand side must be less than or equivalent to length of the right hand side. And Second rule, epsilon is allowed to only the starting symbol. You can't take the epsilon wherever you want. But in unrestricted, you can take wherever you want, but you cannot. And the other one, right? So these are the two rules for the context sensitive grammar. And of course, according to the rule here, type 1, the hierarchy. So you can say that type 1 grammar is also a type 0 grammar. That's the right. So now, as I told you, it must be less than or equal left hand and right hand. So you can take this example here. And if you take the epsilon, that is only allowed to the starting symbol and you're not supposed to take for any other. And coming to the context free grammars, this is the most popular and most fastly grammar. So alpha tends to beta. So the length of the alpha should be only 1. And that too, the alpha belongs to non-terminals. You cannot take any symbols. In both the grammars, left hand side, right hand side, you can take anything. But here, left hand side only one non-terminal is allowed. But right hand side, you can take wherever, whatever you want and wherever you want. No restriction. You have a restriction that epsilon should be only the starting symbol, but here we don't have any such a restriction. You take whatever you want and the epsilon wherever you want. Coming to the last grammar here, the type 3 are regular grammar. So this is the most restricted grammar compared to all the remaining three grammars. And what is that restriction here? For example, if it is alpha tends to beta, the left hand side and right hand side, the length of the alpha must be 1 and it must be in non-terminal. Means left hand side only one non-terminal is allowed, and right hand side beta belongs to only two symbols are allowed. Either it is a non-terminal followed by a terminal, or a terminal followed by a non-terminal, or a terminal, or epsilon. That's it. So right hand side, at most two symbols are allowed. Even three symbols are also not allowed. At most two symbols. If there is only one symbol, must be a terminal. If there is no symbol, also allowed. But if there are two symbols, one must be terminal, one must be non-terminal. You cannot take the repeated symbols. If it is only one, terminal only. You cannot take the non-terminal. If it is a non-terminal, there must be a terminal. If it is a non-terminal, there must be a terminal. Oh, right, like that. Example, you can go with this. So we already discussed about this relationship, guys. So type 0 means unrestricted. We have both recursive and recursive enumerable. If it is a decider, it is a recursive. If no decider, like no halting, then Turing machine. Type 1 context sensitive, languages is context sensitive, and machine is linear bounded automata. Type 2 context free, language is context free, and the machine is push down automata. Type 3 regular, language is regular, and minimal automaton is finite state machine. As we have done, each category of languages or grammar is a proper subset of category directly beneath it, right? Means whatever the rules we have applied for here, right? By writing all these languages, machines, whatever we have given here, so that I completely represented here earlier. So you just apply whatever the subset superset theory to all the things, right? So that is about Chomsky hierarchy of languages. So in the next grammar, we'll see in the second unit, we have discussed many things about the context-free grammars, many like parse trees, derivations, ambiguity, but not for the regular grammars and unrestricted and context-sensitive grammars. Of course, we are not going to deal much about the context-sensitive and unrestricted grammar, but in the next video, we'll discuss what is regular grammar, what are its type, and how can we convert, and some examples of unrestricted grammar that we'll discuss in the next video.